So I sort of have a couple of goals in this talk. One of which, obviously, I have to acknowledge all the people that I have worked with that I'm going to quote stuff from. And this is a mostly whole list, but if you were excluded, I apologize. But the work actually comes from a variety of people at NREL and out of our EFRC, the Center for Next Generation Materials by Design. And I'm going to kind of show you how this has evolved over quite a few years and how it might be useful in accelerating the development of materials and devices towards shortening that 30-year time constant that we heard. So we're going to talk a little bit about the opportunity, the need, and the challenge. So we all understand that there's lots of photons. And that if we could convert them all, we'd have all the electrons that everybody wants to do all the things that we've heard all morning and yesterday from Ernie. However, as we begin to install more, and we're reaching that point in some places, it gets cheaper and cheaper. I'll show you how that has been working. And there's a lot of potential advantages, which we've talked a little bit about in terms of obviously the pollution, sustainability, energy security, and stable low-cost energy for the future. And I point out that we tend to talk in a US-centric version, but we really need to talk in a world context. And the needs for energy storage and energy generation in Indian villages that don't have power or sub-Saharan African villages that don't have power is completely different than what we do with our grid. So keep that in mind. I think we know the sun doesn't shine, at least locally at night, at least not where I live. And nor does everyone have sunny weather. We could say in the US context that our grid is somewhat antiquated. The rest of the world would say completely antiquated. Whether we choose to invest what's now $1 trillion to fix it or not is a valid question. If not, how you go from integrated to distributed is a big issue. A lot of the chemical approaches that we've talked about today already are actually critical if you go into a more distributed local kind of system. I think also we've heard it this morning, we heard it yesterday, really in terms of what we're talking about in terms of just electrons, it really represents only 20% of the total consumption. And so if we really do want to substitute and make that percentage much larger, we really have to think about how you go about doing that. So we can think about the primary energy aspects, where we're talking about sort of 18 terawatts. Electricity represents only about 2.7 terawatts of that. And right now, PV represents about 0.032 terawatts of that. You can look at that as an opportunity and a challenge, or you can look at it as a huge hurdle. I was talking to Harry this morning, and the idea of how you manage to increase your manufacturing power to the point where you can make, Cecina's right, this is somewhat ineffective. If you make the 0.032 terawatts into something that looks a lot more like 3 terawatts is a real issue. So we can kind of look at, there's this interesting bifurcation here, and I like the quote, which is, the test of a first-rate intelligence is the ability to hold two opposed ideas in the mind at the same time and retain the ability to function. I know my children could not do that when they were younger. So the idea is that right now, renewables, especially solar, are a really small percentage of the world electrical power. But if you look at the expanded capacity for the world as a function of time, especially, so this is 2015, it's 20% of the expanded capacity is in renewables. So what does that tell you? It tells you that we're not building a lot of other plants and that the renewables are being built at a much higher rate. So they could have a much higher impact. If you look at what happened in 2016, and this has actually continued 2017, and we expect in 2018, that solar is now 29% of the net expanded capacity. So solar is actually growing very rapidly, which is not too surprising because it's a pretty small number. But the question is, how do you make it big on that scale? How do you change the 1.5% of world PV? Well, one of the things that can help do that, of course, is the cost. And I remember when I first got into PV, and I won't show you where it is on this curve because it's too embarrassing, but you can barely see that. But what people thought is that it would never track along this growth curve. And the two red dots here are real data for where we're at now. And what we're seeing is that the cost really is tracking down as you would expect as the manufacturing goes up. And it's really only in a couple of technologies. But the cost now is literally approaching, this is the module cost in 2016 dollars per watt. We're really approaching 10 cents per watt. And we should achieve that in the next few years. That is miraculous if you remember that, 10 years ago, we were at $8 to $20 a watt. So I think it's actually a good sign for all the technologies we're talking about, that as you begin to scale them, that you really can benefit from the scale. But I think it's also remarkable that a device like PV has now achieved almost parity with other grid-generated power like coal and natural gas, et cetera. If you look, there's another interesting aspect. The solar efficiencies have come up pretty much to near parity, and they're now approaching the Shockley-Queisser limit pretty much across the board. And in fact, I thought that gallium arsenide was one of the most remarkable because it's really close to the Shockley-Queisser limit. And that shows that we're beginning to get our solid-state manufacturing, or at least our discrete devices, much, much better. But if you look at the market is still completely dominated by silicon with maybe a little bit of a spice that's cad telluride. The thin films have not yet lived up to their promise, although they potentially still have lower cost. And now people are beginning to look at how you hybridize silicon with other technologies like the perovskites, where you could actually break the Shockley-Queisser limit but not add a lot of cost to the device. So if you look, one of the interesting aspects is when this all started, the main concern was how do you make the device more efficient? Obviously, the devices are approaching their efficiency limits, at least in discrete devices, not in modules. But other factors have become increasingly important in terms of the overall cost structure for PV. And I think it's interesting. So one is you want to lower module cost, which is actually the device cost and correlates also to the efficiency. You want to lower the balance of system hardware. This is a really big issue, and it's becoming more important over time. You want to improve the lifetime. One thing that we talked about earlier is that if the lifetime, and SunPower is actually looking at a 50-year warranty now for devices. This creates kind of an enigma in society because that's a generational warranty, right? If you turn over a generation every 30 to 40 years, then your PV devices are lasting longer than one generation. It's just an interesting thing to think about. But if the devices really do last much longer than we think they will, then we don't have to make quite so many of them as we begin to have more and more installed PV. So that's important. The O&M costs are an area of opportunity. And this is sort of the Sunshot 2030 utility goal. And it looks like it's pretty attainable within the range of being able to work in these. So we can increase PV substantially. At some point, you're going to have to think about storage. See, George, I actually am going to talk about storage. And if we begin to look at that, so this is annual PV deployment in gigawatts. And this is a recent paper that has come out like 2 weeks ago. You can look at sort of the baseline, which is sort of where we are. What happens if you go to Sunshot 2030? You can think of, the 20 gigawatts. And if you can add a little bit of low-cost storage, you can amplify that by a factor of 2 to 3. And it doesn't matter whether that storage sits with the PV or is somewhere else, as long as you can store those PV electrons for use when you want them. And so there is an immense opportunity. If you look at sort of a sensitivity analysis for storage, what you see is, again, that the capacity, as this is 2050, the capacity goes up substantially with a little bit of drop in storage cost. And I think this is really important. So we can't, the flow batteries, if you can get them cheap enough, lithium batteries, if you can get them cheap enough, hydro storage, PV doesn't really care, right? And actually, we shouldn't care a lot. If we can get the cost low enough, we can have much more impact of the renewables. The real problem is that if you don't, I mean, we talked a little bit about the duck curve earlier. The real problem is that you don't want to curtail your PV in the middle of the day because you don't have anything to do with those electrons. And that's actually happening. Wind is being curtailed a lot because when does the wind blow? Wind blows at night. And we'd really like to have enough storage so we don't have to curtail the resources we put out there. That just doesn't make any sense in the big picture. So some of these things require new materials. I wanted to sort of put a context on how you might think about the whole thing in terms of materials development, because we've already heard a lot about new materials. And I'm an old-style chemist, but I've been educated by new-style theorists to say that there's a better way to do materials development than what we used to do. And so we can think of two different approaches here. One is sort of designing by design principles, i.e., if we want a better energy storage material or a better transparent conductor or whatever, we can say what is needed for that, and then we can do the computational analysis, and we can map that against known materials. But the other opportunity, and maybe the larger one, is that we can look at unknown materials, and we can first see which ones will be stable, and now we can begin to address synthesizability a little bit. I'll talk about that. And then we can map it against these same properties, and if we're good, then we combine these two, and we can accelerate the development of new materials for actual applications. So how might this work? I'm going to show you a couple examples, solar fuels, and batteries and more, since we're not talking about lithium batteries. So we all know about photoelectric chemistry. We know people have been trying to split water for eternity. Maybe that's a bad way to say it. How old are you, Art? No. So the thing is, we can pretty well specify what we'd like to see in a water splitting material. And then we can look, and some of us a long, long time ago did empirical models to try to understand the material space. And so we can kind of identify the critical factors. And now we can begin to do computational analysis of those critical factors in a way that we couldn't do 10 years ago, 5 years ago. So, for example, we can begin to look at, if we say everything is at the point of zero charge, we can begin to look at what you want in a conduction band maximum for a photoelectric material. So this summarizes a whole lot of calculations. You can look up the paper. But what I'd like to illustrate is so we can kind of step through a functionality that we're after, in this case, photoelectric chemistry, and we can look at sort of materials that might meet those criteria. And so we can calculate the absolute valence band maximum, conduction band maximum pretty well. Minimum and maximum, excuse me. But if we can look at, say, the tin oxide case, we see there's big variations with HKL. So what we'd like to do is learn how to do this as a function of the orientation of the surface. And we're beginning to be able to do that. This shows the calculations for tin sulfide, which is a potential photovoltaic material. And you can see that we can get substantial variations as a function of the orientation of the surface. So if we incorporate that, then we can begin to try to map the theory onto electrochemical measurements And that'll give us an idea of whether that material, one, sits where we want, and two, whether it might be a good photoelectrochemical material. So coming back to this, we can map against that, and we can actually say that for a certain set of materials, they ought to be able to do photoelectrochemistry like we think, and it works. And you can see that the error bars here, which are represented by the bands, are actually pretty small. So we've now been able to develop a theoretical framework for one of the ways we want to do energy storage, in this case, making hydrogen. And so then how do we search? So Christine Pearson was very nice to send me a whole bunch of slides. And we can do things like couple to the materials project, which uses first principles calculations to identify materials. So we can begin to look at sunlight to fuel materials. We set a set of criteria, so based on the kind of calculations that you just saw. So valence band maximum within certain potential, band gap, and a stability at a particular pH. And then we can begin to map that against real materials. And obviously, if they don't have all yeses, it's probably a bad sign. So you can take a big set of materials. You can begin to look at these criteria, all computationally, to sort out what you want. Look at the band gap. Look at the band edges. Look at the stability in water, which we now can calculate the stability really well. We can do Porbet diagrams as a function of both the solution concentrations and the surface energies. And so we have a pretty good idea whether they'll actually be stable in water. And this results in a small set of materials. So then we can take those materials and we can think about, the kind of arguments that we've heard about which ones might be useful, which transitions might work, and then we can make those materials. And we'll get to that in a second. And we can begin to actually see which materials might be good photoelectric materials. All based on this computational framework that we created originally. And so the catch, of course, is if you identify a good material, then you have to be able to make it. Okay? And so this is only maybe a third of the journey. My experience has been that the theorists are very good at telling me what materials they want, and then I go to the lab and can't make any of them easily. So the question is, how do you synthesize materials? Now, we all know there was a basic research need in material synthesis. It was very well crafted, and I think it brought up some of the key issues. So in this sort of diagram, we sort of have the targeted functionality. We can begin to identify what materials we want, and then we somehow have to be able to synthesize it. And we want to be able to get the right polymorph, get the right surface orientation, ideally. So how do we go about this? So one of the systems that we have looked at is the manganese system. And I like the manganese system because it's incredibly diverse. Let's see, it's that diverse. So we can think of it as an energy storage material. It is in alkaline batteries. It's in lithium-ion batteries. It does all kinds of cleanup. It's a photocatalyst. It works in supercapacitors. So understanding the system and being able to select out a particular polymorph and make it is actually really a key thing that we want to be able to do. So the first thing we knew is that we didn't do very good on magnetic materials, on doing the DFT, and so we worked with the Temple FRC, and they came up with a scan algorithm which allowed us to do much more accurate DFT calculations of the band edges and the energetics. And that was enabling for us to then go look at the synthetic framework where we might actually make these materials. So I would never have believed a couple of years ago that you could draw this kind of diagram, but it works. So what we did is we looked at the radius of a particle as it begins to grow. We looked at a concentration of an auxiliary ion, because a lot of these things grow hydrothermally, and this was all done hydrothermally, where they are enabling, and we looked at the pH as factors. And this is a computationally generated diagram, okay? And so what we find is that small surface energies result in fast nucleation, not surprising. That metastable phases can form kinetically and be stabilized kinetically, and that off stoichiometry favors particular phases. And then once a phase forms, if we're lucky, topotactic reactions are going to lead to an increased growth of that phase. And all of these things turn out to actually work. So, Dave. Yes, I know. Please use the mic. I don't usually need a mic, but they're recording. So I'll give you a couple of examples in my last few minutes. So one of the materials that I like that came out of this is there's a phase called totorochite. And this is typical of some of the things that we found. I can go on eBay, which I did, and you can buy samples of totorochite, mostly from Pakistan, it turns out, but that's sort of irrelevant. But if you try to actually buy totorochite itself from any chemical supplier or even synthesize it directly, there's no easy way to do that. Why do we care? Well, it turns out totorochite is very fascinating. The size of these pores are about 11 angstroms on a side, making it having one of the biggest pores, so for catalysis, for water purification, for all kinds of things. For energy storage, this is a very interesting material, only if you can make it well. And so we couldn't. Nobody could. So they theoretically modeled it, and they modeled it against added sodium ion and added potassium ion. And I know it's a kind of busy figure. I hate doing these kind of figures myself. But if you look at the tan line here, the tan line is the totorochite phase. And so what it says is that in a particular regime, the totorochite phase should be the most stable. And it's a theoretical prediction which actually is experimentally realized. So we went to that regime, we added the right concentration of sodium, and we made 100% pure totorochite phase. Once we had that, we could do something very interesting. We actually annealed it at high temperature, up to about 600 degrees, and what we find is that you lose all the water that's entrained during the synthesis process, but the totorochite phase stays the same. So now you actually have an empty matrix of holes, and we're beginning to look at what the material can do. Another example is the post-Spinel phase was theoretically predicted to exist and had never been made at all. And given where they told us to go synthesize, we were able to make that phase. And so I think there's a sort of theme here that says we can describe a functionality, we can describe what kind of materials might actually work in that functionality, and as we begin to develop better tools to understand synthesis, we can begin to actually make those. This could dramatically accelerate the rate of materials development. And I think that's what that all says. So I'm done, and I'm happy to answer questions.